So I will introduce Dr. Scott Jackson,
All right.
who is our one of our board members. He is also been an associate at Mount Cuba for a very long time. He is a professor at Villanova, not teaching astronomy. I should.
Well, actually, I sort of sneak in some astronomy in all my chemical engineering lectures.
Well, there you go.
Yeah.
We just love science. So any type of
The
science.
students love the astronomy. They hate the chemical engineering.
Of course they do. So without any further ado, I'm going to go ahead and turn the evening over to Scott. And like I said, if you guys have questions, put them in the chat box and I will make sure they get answered for you.
Okay. Thank you very much, Kim.
Yourself.
All right. So what I'm going to do is I'm going to share my screen so you're going to actually see the presentation going on. And actually, if I'm good about this, and yeah, I am, I can actually write on each of the slides. Isn't that amazing? So the thing is titled Fire and Ice, and it is a lot about basically volcanoes will stay to the Earth initially, and then we'll talk about what makes volcanoes on the Earth, and then we'll look at other planets to see if those same conditions are apparent in other planets. And then finally, is there other kinds of volcanoes in the solar system? The answer is absolutely yes. And it may surprise you what we find as we go through the solar system. So these volcanoes in the water that in a solar system, you think, what does that have to do with reality? They aren't related, but in many ways they are, and we'll get to that shortly, okay? So volcanoes in our solar system. So we'll talk about a lot of famous volcanoes on the Earth and how they are made, and it has a lot to do with plate tectonics. And then we'll talk about our moon, and then we'll talk about Mars, which is very relevant. Consider the probe that just landed there. And we'll talk about Venus and Mercury. And then finally, the moons of Jupiter. And Io specifically is a very interesting object in our solar system. It's a moon of Jupiter. It's the closest one in. And we'll talk about some of the most active volcanoes in the solar system being in Io, okay? And then finally, we'll talk about ice. So at some point in time, things, this Io volcanoes that we'll talk about aren't really that hot, okay? But once we get out further, hot is a relative measure of things, right? So cryovolcanoes are really important in further out in the solar system. And you'll see about this in these two examples. And let's talk about famous volcanoes on Earth. So the first question is, have you ever been to Hawaii? And Mauna Kea and Mauna Loa certainly are on the main island of Hawaii. This actually shows some of the cinder cones. This is an overhead shot. And I think this is maybe some astronomy stuff, but here's more cinder cones. And here's the astronomy establishments up on Mauna, I think it's Mauna Kea. And then this picture here is a picture that tries to simulate the actual shield volcanoes that have erupted from the base of the ocean and coming up. If you take from the base of the ocean up to the top of Mauna Kea or Mauna Loa, they're some of the tallest volcanoes. They are the tallest volcanoes on Earth, not necessarily in the solar system. Okay, sort of interesting. And here's some more pictures. This is the smiley face of, I think it's Mauna Loa. I'm not certain, but this is an active volcano, and that volcano's spewing out lava. And these houses, unfortunately, on Hawaii are being destroyed by the march of lava coming down from the volcano. This actually,
I think that's Kilauea, Scott.
Oh, Kilauea. Okay.
Yep.
And this actually shows you some of the areas that were inundated by the lava being, wiping out areas. And this is particularly area. So this is actually new land that was produced by, I believe it's Kilauea, right not too far from Hilo. Okay. Another volcano that actually is very important in history is Mount Vesuvius. Okay. And in the Roman times, it caused basically Pompeii and actually one next to him, Herculana, to be utterly destroyed in a thing. And in fact, if you go to Italy, one of the great tourist attractions is to travel to Pompeii and see the remains that they have excavated out. It's pretty remarkable what you'd see. But the fact of the matter is this volcano is still active, okay? And here is, in fact, Naples, right at the base of it. And there's a lot of people here, like a couple million people. And if this thing blows off like it has in the past, these people are at risk. And matter of fact, it doesn't show here, but there's actually a wall back here that is an attempt to stop any lava that may come down from this side of the volcano, and that might wipe out the city down there. So another great example is Mount Tambora in Indonesia. It erupted in 1815, and that's the same year that Frankenstein, the novel, was written, in part because it caused the year without a summer, okay? So enough ash was flown up in the atmosphere that it reflected a tremendous amount of sunlight, and it caused dramatic weather changes. Now, that only happened perhaps for about a year, but that gloomy kind of condition caused the author of Frankenstein, I can't remember who the person is, to actually, what's that?
Shelley.
Okay, to actually write Frankenstein. Supposedly, that's the story. That's the urban legend. I think that's probably right. Okay, Krakatau. That's probably a little bit better known. It happened in the late 19th century. It blew up and actually knocked off half the island. And this is a very classic kind of cinder cone. You can see here it's still an active volcano. Yellowstone. Been to Yellowstone? If you look around and said, there's no volcanoes here. Holy smokes. That whole area, you may not realize, it's basically the remnants of a gigantic cinder cone. So right here, right around this area, is where all the geysers are. These are the geyser fields, the Old Faithful's right here, and there's a bunch of other geysers that are right around in here. So this is the north entrance. No, this is the north entrance, as I recall. This is the south entrance coming up here. And here's Yellowstone Lake. It's interesting that in the last few years, Yellowstone Lake has actually tipped a little bit by about 3 or 4 feet. It's like, holy smokes, what's going on? So we know that in the recent past, it was a super volcano, that it erupted. And if it were to do what it did back then, it would cover most of the United States under a covering on the order of 6 inches to several feet of ash. So it's a very large caldera. It's not the only one in the West that's still considered active. The Valle caldera, which is behind Los Alamos, is also another super volcano. It's actually second smallest to the Yellowstone one. So it's like, what the heck's going on here? Should we be afraid? You shouldn't be afraid, but you should be aware that there's still hot spots in the crust that's causing volcanic activity in the Earth. Mount St. Helens, okay, another kind of shield volcano, and this whole side blew out back in what, I think it's 79 or 80, something like that. I can't remember the exact date, but very dramatic to say the least. The classic movie of it blowing out is still imprinted in my memory, to say the least. Let's talk about Yellowstone. So Yellowstone's right here, okay? So what's happening is there's a hot spot under the crust being our North American continent. It's actually floating on basalt, and there's a hot spot right underneath that's coming out of the basalt. And as this crust of basically granite is floating on top, there's this hot spot is moving. So the hot spot used to be over here, and in time it has moved across the bottom of Idaho, and it now resides where Yellowstone is, okay? Hotspots are very common. Hawaii is a result of hotspots. You can see a chain of islands that was produced because the hotspot used to be much further west than apparently much further west, and it's moved to the point where the main island of Hawaii is now, okay? Same kind of concept. What causes hotspots? Not so certain, okay? But there's other hotspots that occur. This is a typical structure of a volcano here on Earth. So you have a very strong molten lava coming up. It erupts. It may have side arms coming up here, and basically it comes out as a shield. There's a very definite angle of repose for materials coming out. That tells you something about the strength of materials and other stuff. It's engineering. You don't want to know about that. but it's ultimately caused by something that's molten in the core that comes up to the surface and expands out and comes out. It's not necessarily, there's not a great understanding of exactly when a volcano will erupt or when a new one will come into play, okay? This is a great overhead shot. So we're looking straight down. It's one of the islands along the Aleutian chain in Alaska. And you can see how nicely symmetrical this one volcano is. And it's erupting in this case and spilling out its guts into the ocean here. And there's another one right next to it here. And there's another one right over here too. So it's what's different about this as opposed to a hot spot for others like the Hawaiian Islands is that it's under a subduction zone. And in fact, most of the west coast of the United States is under a subduction zone. You're sitting there going, what is a subduction zone? Sounds a little strange. It has everything to do with plate tectonics. So what happens is there's this North American plate here that is basically granite. So it's lighter weight than what's the basalt. And there's these plates here. In this case, there's a partial melting and there's spreading apart of the ocean crust, a mid-oceanic ridge that's formed. And it's being pushed up against this lighter crust that forms the North American continent. And it's actually being pushed down underneath it. A lot of friction is being caused. That friction causes melting of the rock, and that melting causes earthquakes and also volcanoes along there, okay? And in fact, it ultimately forms the ring of fire around the Pacific that includes Japan and Indonesia and California coast, okay? So the question is, so this is plate tectonics. It's a theory that was generated back in the early 20th century. It wasn't really accepted until the 1970s, okay? But it's generally accepted that the Earth clearly has evidence of plate tectonics. A really good example is the mid-oceanic trench or mid-oceanic ridge in the Atlantic Ocean, where in fact the North American plate and the African and Eurasian plate has been moving apart from each other. And in fact, when you look at a globe, you can see how the South America and Africa sort of fit in each other. And that's actually true, that they used to be one part of a gigantic continent and they were ripped apart as this mid-oceanic ridge was formed, and they're sort of on a conveyor belt being pushed away from each other. But when they do get pushed away from each other, that causes friction, and consequently molten material is generated under the crust and then is forced out, and we see volcanoes and earthquakes, okay? Question is, do we see that kind of process in other planets? At this point in time, the general belief is no. There's a possibility that it's occurring on Venus, but it's not so clear, and there's not any strong evidence, okay? So let's look at our moon. The moon was actually produced because there was a protoplanet that slammed into what basically was proto-Earth, and when they slammed into each other, out came what was the moon, our moon, and what we see left behind were these mares, and it's like, oh, I wonder what's going on there. Okay, that's not quite volcanoes. There certainly was molten lava that was spilled out, in part because that was the violence and the friction caused by the collision of this protoplanet and the protomoon. And certainly there's lots of craters, but those craters aren't they aren't volcanoes. They are in fact impact craters, okay? There's many extinct volcanoes, but really they're sort of mares. So they're not kind of volcanoes we're used to thinking in Earth, okay? So the mare are in fact not like volcanoes on Earth. It's because this process that caused the moon and whatever volcanoes occurred are essentially extinct on the moon. In fact, they have been able to look at the structure of the moon, and there's no molten core like there's a piece of it that's partially melt right here in the moon, but it's much basically dormant compared to the Earth. The Earth has a very dynamic molten core that gives us something very important. That's our magnetic field here on Earth, and that saves us from the solar wind and radiation. But there's nothing like that on Earth. On the moon, there's no magnetic field, or very, very little magnetic field on the moon. And we know what the structure of the moon, in part because there's seismographs that have been placed there by the Apollo astronauts, and we have lots of information about what's going on. They've been able to model it, and they pretty much know what the structure of the moon is. So consequently, there's no really kind of molten material there that could cause active volcanoes as we know now. Okay. However, there are interesting features on the moon. There are these dome hills on the far side of the moon that may have been, past tense, may have been caused by lava pushing up underneath there and causing this dome structure. This is meant to show a dome right here. And yeah, there's a hill here, there's a hill here, there's a hill here, but maybe there's something pushing up underneath it. You know, I guess you have to have a wild imagination or maybe some other data that would support this. So, but there is one other thing. This is a recent, I say recent, this slide is about 3 years old, so it's at least 3 years old. There is evidence there's actually a silicate volcano underneath the backside of the moon that they have detected by a NASA probe. And how real this is, what it means, don't know. But again, that could be an upwelling of lava that has since long ago frozen, so there's no really active volcanism on the moon. Certainly, there's no plate tectonics. There's no segregation of materials. There's no subduction zones like they're in on Earth. There's nothing to really cause a movement of the crust like there is on the Earth. The Earth has an active, very strong heat generation from its core, and that heat has to be removed somehow, and that causes the conveyor belt that moves the continents around. Nothing like that on the moon. Okay? Let's talk about Mars. All right? This is a great shot of Mars. This is the Valles Marineris, as I recall. And this is the largest canyon, if you will, in the solar system. It's about 5 times the size of the Grand Canyon here on Earth. It's incredible at both depth as well as length. Not certain what it represents. Somebody says, "Oh, that could represent a breaking apart of the crust." Not clear that that's what it means. Okay, so there are gigantic volcanoes on Mars, and we'll see them shortly. Olympus Mons is in fact the largest found in the solar system. At least that's what I understand. It in fact would cover the entire state of Arizona. It's a huge mountain. Okay, it is in fact similar to compositions here on Earth, but it's not active. It is extinct. There's nothing going on. Okay, there's really very little magnetic fields on Mars, and there is a probe that has landed on Mars that is trying to measure Marsquakes in order to understand the structure. Bottom line is basically the core of Mars is essentially frozen. There is very, very little, almost no magnetic field compared to the Earth. So consequently, the solar wind is unimpeded when it comes and hits the atmosphere of Mars, and it has eroded the atmosphere. At least that's the current theory. Has eroded or sputtered away the atmosphere of Mars, and that's where there's virtually no atmosphere. That's what scientists believe. There's very little atmosphere on Mars, simply because the solar wind has eroded away because there's very little magnetic field. There's not a strong magnetic field like there is on Earth. The magnetic field actually causes solar wind to be deflected around Earth and gets away, and we don't get the solar wind impinging on our atmosphere, and it doesn't get sputtered away. Mars did have a molten core in the past, and it did have a magnetic field in the past. And we can see that as residual magnetism in some of the rocks that we have seen. But right now, there really isn't anything. And that molten core did, in fact, produce these volcanoes, including Olympus Mons. But again, they're all extinct, okay? So this is an overall, think of it as a map of Mars, okay? And there's a lot of cool things that are going on. So this is up here is the North Pole. All this white stuff you see up here is in fact frozen carbon dioxide. So the North Pole in this case is in winter, okay? Down here, you don't see the South Pole, but it can tip back and forth. It's a lot like Earth. And when it's in winter, it'll get frozen carbon dioxide. There is lots of frozen water up here, and there's also lots of frozen water down here. And they believe there's probably a lot of water even at moderate latitudes closer to the equator, not necessarily at the equator. What kind of water is now the question, and whether there's life that could be hidden in there is one of the real questions they're trying to understand. Certainly there are clouds in here, and then right here, you can't tell very well, but there's actually lots of volcanoes as well, okay? So this is from the Global Mars Mosaic, and the North Polar Cap is at the top, volcanoes are at the left, that's a volcano over there. And then there's that Rift Valley that I showed just a couple slides ago. And then there's and then there's the clouds. And there's Olympus Mons, okay? So cool. I mean, this looks just like a volcano on Earth, but this is the size of Arizona. It's huge. So this is all going downhill. This is all going downhill. And you're sitting there going, what the heck is this stuff, right? Well, that's where basically the lava has come down. It's frozen, and there's actually a very sharp cliff at this point in time. This is the caldera, okay? There's actually these are impact craters right here. And in fact, they can sort of guess the age of this because the impact craters on here, the density impact crater, there's not a lot of impact craters, hence it's not necessarily all that old, but it is somewhat old. And these craters, though, are not impact craters. They are due to the volcanic activity, okay? But again, it's extinct. It's not doing nothing, but it is the largest volcano in the solar system, okay? Olympus Mons, pretty cool. Here is the, I believe this is the North Polar Cap. This white stuff, you say, oh, that's water, that's frozen water. No, no, no. That's carbon dioxide, okay? That's frozen carbon dioxide, dry ice, okay? Yes, there is actually a lot of water underneath there. And this is an attempt at showing the thickness of water. This is measured by radar as a probe went overhead that it shot radar down. And basically the hydrogen on water will give a very distinctive signal coming off the radar. And you can see that the nominal thickness is 2 kilometers here. And then this is the thinnest stuff way out here. So that's actually a lot of water trapped underneath the polar cap. And this is from the Mars Surveyor, extremely cold temperature ice water. If you actually do a cross section, you can look at the radar map, and what you see is that this stuff right here, below here, is rock. It's called base rock. Above here is actually layers. You can sort of see the striations alternating between frozen water and basically dirt or dust, frozen water, dirt, and dust. And there's a lot of work to try and figure out why this layering is occurring. This, again, is a North Pole, okay? Essentially, very similar kind of process is occurring on the South Pole. And you're saying, okay, what does this have to do with volcanoes? Because it's fire and here is ice, okay? Okay, so there's nothing that looks like a volcano here, but you'll see shortly that there's a lot to do with volcanoes, volcano-looking stuff that has a lot to do with water a little bit later on, okay? The fact of the matter is, and I throw this in just to, gee, that's amazing, is that there is enough water that's trapped in the poles that if it all melted, it would create a shallow ocean about 36 feet deep across the whole of Mars. That's an amazing amount of water. It's not necessarily fresh water. It's probably very salty. So, and it's not clear at all to NASA whether they could actually land on this polar cap and get something, but it appears to be there. And this is again from radar and some other telemetry they have, okay? There's also other evidence of water on Mars. There's glaciers, clearly glaciers on Mars. So this is a glacier right here. This basically is flowing out this way. This is a side moraine. There's a terminal moraine here. Basically, you got a sloughing off of this material. The glacier is not, in this case, just ice. It's a mixture of ice and rock. Same thing for this thing. So this has sloughed off and it's flowing this way. Again, a lateral moraine here and probably a terminal moraine. Stuff has been pushed out. That's what a moraine is, just stuff that's pushed out by the ice. But clearly this had moved in the past. Whether it's still active or not, that's another question. And more observation will tell us whether these things are in fact active or not, whether they really are truly moving. All right. Let's talk about Venus. Okay. So Mars is very cold, very out there. Okay, we saw clear evidence of volcanoes, no evidence of plate tectonics. That is, there's no obvious indication that there's plates that are moving around on conveyor belts like there are on the Earth. But here's Venus, shrouded in clouds, right? Runaway greenhouse effect, right? And I say fire here because if you can get through these clouds, you start seeing something that's very dramatic. So this is actually, I think it's in ultraviolet light. I may be wrong about that, but it allows you to see the clouds. If you took a telescope like the one that's behind me here and looked at Venus, it would just see this brilliantly white surface. You wouldn't see anything basically. It's just this white thing. So you don't necessarily see this unless you choose a different spectrum of light. And this thing, I think this is ultraviolet. Okay, so it's a very dense atmosphere, completely clouded over. The really only way to see the surface is in fact by radar. Ironically, the one facility that has been used a lot to actually do radar mapping or help to do radar mapping, and usually you have to do two pieces, is the Arecibo antenna down in Puerto Rico. So that's out of commission, but we'll still be able to figure out a way to do these kinds of things, okay? And in fact, the Chinese say, oh, we got a much bigger antenna than Arecibo. Yes, they do, but they don't have the ability to use it as a radar. What's unique about Arecibo is that it had the structural support to actually put in the thing that made it into a radar dish. The Chinese actually don't, believe it or not. But be that as it may, okay? So it is interesting that radar has recently seen evidence of lava flows and volcanism. Now, I will tell you, unlike Mars, Venus is sort of at the short end of the stick. People are pretty much ignoring Venus, although recently, I think last year, it came out that, oh, I wonder if there's looks like a signal of phosphine, pH, I think it's 3, a gas that there's no way could be made without an organic way of doing it. That is some sort of life to produce phosphine, okay? And it's like, what? So they're not certain if that's what they're seeing, whether they're seeing phosphine. But if there is phosphine there, then holy smokes, does that suggest that there could be life up in these clouds where there's a more moderate temperature? Because certainly at the base, our concept of life cannot exist on the surface of Venus. It's just too hot. Life as we know it could not exist. It's at about 800 degrees Fahrenheit. It would kill everything that we are aware of, okay? But up in the clouds, perhaps in the distant past, very distant past, life did evolve to a certain extent. It might have been microbial, and maybe it got up in the clouds and it still exists there. Who knows? Sort of interesting. Don't know whether I believe it or not, but the bottom line is we still do see evidence of lava flows and volcanism. Here is a picture. You strip off the clouds, and this is basically a radar image, and you can see all sorts of interesting stuff here, okay? This here is essentially a 3D image. I want to say it's of this thing right here. You can sort of see it's pretty small. It looks like there's streamers coming out of this mountain right here. It's like, huh, I wonder if that's a volcano. So in general, it's believed there is volcanoes on Venus. And this is an example of that volcano. It's coming down, and it sort of like a cinder cone. And this is probably a lava flow coming out of it. And there could be lava flows right in here on Venus as well. Are they active? That's the $50 million question. So there is work going on to try and take another snapshot of Venus under the clouds to see if things have changed from what they saw before And hence, if things do change, then it says, oh, so maybe there is active volcanism. There's no, from the analysis people have done from images like this, it's not clear there's any plates that are moving around, plate tectonics like there is on Earth. I gotta believe it, at some place in the universe, there are other planets that show conveyor belts that are moving plates around like there are on Earth. It's not clear that that's happening on Venus at all, okay? There is a good chance of volcanism. The mechanism uncertain, but we just go ahead, okay? Radar images of Mott Mounds. This is Mott Mounds, and it's not clear if it's active. It could be. You need to take another snapshot, okay? Okay, Mercury. Right. So first evidence of Mercury. At first look at Mercury is highly pot-marked. It looked like the moon. It looked like an ancient surface. Very high crater density. It meant, okay, it's very, very old. The more the craters, the older the surface, okay? But they looked more carefully. Mercury is a very old object, just like the Earth, right? And certainly there's no air. And some of the first satellites looked like the moon. On the sun side, it's very hot. On the back side, it's very cold, okay? And the fact of the matter is, at one point in time, it's called an inferior planet because it's inside the orbit of Earth, okay? It's always close to the sun from our perspective, okay? Venus is also an inferior planet. But let me tell you, if you lived on Mars, Earth would be an inferior planet. Oh my God, Earth's an inferior planet. Oh, that's terrible. Any case, so the fact of the matter is Venus and Mercury show phases much like the moon. And for Galileo, that was very important because that was a censure. That said, Venus goes around the sun. It doesn't go around the Earth, okay? For Mercury, it's very difficult to see. You have to have a very clear horizon, and you have to know when Mercury is at the maximum distance away. It's called maximum elongation away from the sun. And it's usually when it's up at a very high angle instead of a low angle. So there's very specific seasons you want to look for it. It is interesting that there is evidence of some sort of extinct volcanoes, and it even looks like there's faulting going on, but it's not the kind of faults that we would see from Earth. In other words, there probably were quakes on Mercury, but not caused by the same things that cause them here on Earth. Okay, so let's take a look. This happens to be basically on upwelling underneath the crust. This is believed basically to be some sort of caldera. These are just impact craters on the flank of what would be a volcano on here. This is Messenger spacecraft, so this goes back a few years. And this is actually a diagram. So this thing right here is this thing right here. There's this impact crater. There's that impact crater. And this is the extent of the dome-like feature. So, okay, maybe there's some upwelling. Maybe there was actually a caldera. Maybe there's something going on. And more importantly, which is really cool, this is an overthrust fault. So what an overthrust fault is the same thing as a subduction zone. So you have the North American plate here, and you have the Pacific plate that's going underneath. That's essentially like an overthrust fault. That's what's going on here. It's like, oh my gosh, there's plate tectonics on Mercury. No, there's not, okay? What's happened is Mercury has gotten cold and old and shrunk in its old age. And when it shrinks, guess what? The crust has to go somewhere because the crust is already cold. And what happens as it shrinks, it's a little bit like, I'm trying to think, like an orange or something like that. As it shrinks, the surface actually crinkles, and that's what you see here. Basically, it has to give someplace. So consequently, as the core shrinks because it's cooling down, the surface is saying, oh, I got it. And it has a lot of stress, and all of a sudden it breaks over and it lays over on top of each other. That's exactly what you're seeing here. And matter of fact, this crater right here shows it really well. You'd expect this crater to be nice and round, and it's not. It's cut off, okay? So again, this is like what's called an overthrust fault. There's another example right here of another overthrust fault. It's not plate tectonics. It's not volcanism. It doesn't generate volcanism. It's just an indication that for Mercury, the core has cooled off and has shrunk, and the crust has tried to compensate for it by basically breaking up and compacting itself by these faults. Okay. Jupiter. Ah, that's interesting. Well, Jupiter doesn't have a solid surface, so we can't have plate tectonics there. But this is a great picture. Here's the great red spot, which has actually become the great pale spot. And it's actually grown smaller. Grown smaller in the last few years. When I was a kid, back, eons ago, back when cavemen drew on the caves, this was very easy to see in any telescope. 6-inch telescope, boy, it would just stand out. And I got bored looking at it, right? Now it's like, it's a real challenge to see it because it's so pale and it actually has grown small. Okay, that's a side kind of thing. Obviously, Jupiter is the largest planet. It rotates actually pretty quickly, which makes it a great object to look at night, especially in summer nights. You can, if you have a long night, you can start off and you actually almost see a full rotation in one night if you're willing to stay up all night, and depending on where it is, okay? It's a giant. It would float on water or close to floating. It is certainly visible in a pair of binoculars, but you have to hold them really steady. And there are 4 major moons. Those 4 moons were discovered by Galileo, and he recognized that they going around Jupiter are clear indication that there are other things go around something other than the Earth. And here's a good example of these 4 moons that are going around Jupiter. And boy, to him, that cinched it. It wasn't an Earth-centered universe, okay? And one of those moons is Io, and it's the closest one in to Jupiter. So what happens with something like Io, because it's so close to Jupiter, it sees a lot of tidal forces. The Earth sees a lot of tidal forces, okay? So because Earth interacts with the sun and the moon, we see it as water moving around. So you get high tides and low tides, and it confounds anybody trying to figure out when they're high tide and should be a low tide. You look up where the moon is and the Earth is and the sun. It doesn't make any difference. That doesn't make any sense. There actually is some rhyme and reason to it. On Io, it's a lot different. There's no water on Io, but what there is sulfur volcanoes. So what's going on is that Io is so close to Jupiter, and the tidal forces are so much higher compared to Earth. There's a lot of frictional heating. So Io actually has a lot of sulfur associated with it. And because of this frictional heating, the sulfur will actually come up, and it gets to such a high temperature, it's not really that high. Sulfur is actually a pretty volatile material. If you get it up to about 170 degrees, it'll actually vaporize, depending on what the pressure is. But it'll vaporize, right? 170 degrees C, that's not very high, okay? It's not like iron that you have to get to like 600 or 700 degrees C. So the sulfur comes up, it actually makes sulfur volcanoes, and it spews out the sulfur. What's amazing is the tenuous atmosphere that's around Jupiter, in the space around Jupiter, has a lot of sulfur, and it's all coming from Io. Okay? Pretty cool. Right? So it's totally different than the Earth, Moon, or Mars, or Mercury. Okay, so here's Io. This is a backlit side, and here is one of the sulfur volcanoes erupting. And you can see it in silhouette. The light from the sun, which is over this way, the sun's off in the distance behind my screen, is illuminating this eruption of a sulfur volcano, and it's spreading material out onto the surface of Io. At the same time, you don't necessarily this, but there is actually sulfur being pushed out into space around. There's a very small fraction, and it's basically clouding the space between Io and Jupiter with sulfur, and we actually detect it with spacecraft. It's very often it's ionized, and it's a very remarkable kind of things. If you look down overhead, this is what you see. So here's the caldera, here's the lava flows. It's not like rock what we think about. It's actually sulfur coming out. It's pretty cool, to say the least. So this is a mountain here, and there's basically sulfur coming out, and in this case, there's actually sulfur spewing out. It's a lot like a volcano on Earth, but totally different. The frictional heating It's not caused by plate tectonics anymore, like on Earth. It's not caused by a hot spot that we still don't understand what's causing that. It's simply caused because Io is so close to Jupiter that the pull of Jupiter on the near side versus the far side, the pull on Io on the near side versus the far side actually causes a lot of heating, frictional heating, and that causes the sulfur to become molten, gives its vapor pressure, and it breaks through the surface and causes volcanoes. This is a volcano, this is a volcano, there are hundreds of volcanoes on Io. So there's more active volcanoes on Io than any place in the solar system. Pretty amazing, to say the least. Right? So here's another shot of Jupiter's moon. Here is Io. Each one of these are volcanoes. There may be small, some large, okay? And this orange color is real. It's sulfur. Pretty amazing, right? And here's Europa. All right? And if you look at Europa, you say, well, okay, there's a crater here. There's not too many craters, like hardly any at all. It's like, what the heck's going on? There's no craters on Io either. So you go back to the thought, well, the density of craters tells you how old the surface is. If there's no craters, it says it's a fairly new surface. The surface of Io is very new. There's no craters. These are all volcanoes. You look at Europa, which is the next one out. So it's Io is the closest one. Europa is the next moon out. And it's like, where's the craters? There's only one that we can see in this photograph, but there's all these things going on here. What's happening? Europa is actually still has a little bit of frictional heating, okay? What we see on the outside, we know, is basically frozen water. So it's a gigantic frozen water shell, but what's underneath is an ocean of water. And what we can tell, I don't know exactly which area it is, but there's actually screenshots that go in, and you can actually look at it and you realize it looks like puzzle pieces that are misaligned. And you can actually see icebergs that have broken apart and moved around. And so you realize, holy smokes, these are basically fractures on the surface of this ice. And underneath there is something that has to be liquid because these pieces have broken apart and moved around and then refrozen, okay? And in fact, as a result, there's very few, if any, maybe one or two craters, because the surface is always renewing itself because it breaks apart, water flows up from underneath, it freezes again, and all of a sudden it erases any indication of craters, okay? Pretty amazing. That's why Europa has a lot of interest because, gee, I wonder if we drill into this frozen surface, we get into the water, could be life there? I don't know. Who knows? Sort of interesting. Everybody's looking for life everywhere. All right. So Io has many sulfur volcanoes. Europa is coming from frozen water ice, and it may be a great place. Unfortunately, there is no volcanoes on Europa, but we will see shortly that there are volcanoes, but they're not sulfur volcanoes. They're not lava volcanoes like they are on Earth, but they're other kind of volcanoes. Saturn, great picture of Saturn. No volcanoes on Saturn. Again, another ice giant. This is a great picture, right? You can see the very detailed structure of the rings, sort of cool. What's neat is when Galileo looked at Saturn, he said, oh, there's 3 planets touching each other. So he saw a planet here, he saw a planet here, and he saw a planet here. He had a really bad telescope. I mean, for what he did, it's remarkable what he could see and interpret, okay? But his optics weren't very great. So he was not able to discern the fact that these were rings going around. Rather, he saw this very bright patch of light over here and says, oh, these are 3 planets stuck together. That's remarkable. And it took a while before somebody said, no, Galileo, you're full of it. It's actually rings, okay? And now we know there's lots of rings in the universe. So it's a great ring planet. Galileo thought it was 3 globes together. He had a bad telescope. There's cryovolcanoes, not on Saturn, but certainly Enceladus, I cannot pronounce it, Enceladus and possibly Titan, two of the moons of Saturn. Let's talk about Enceladus. So here's the Cassini spacecraft, comes along and see Enceladus, and all of a sudden, again, it's in silhouette, so the sun is back over here, it's into the screen, and you see these jets coming out. What the heck's going on? And some further analysis says, well, these are water jets. So what's going on? So in some ways, much like Io and Europa, Enceladus is relatively close to Saturn. There is also frictional heating. It has a lot of water, and what's happening is the water is being heated by frictional heating again, and it's I'll say boiling up. It's causing some vapor pressure under the crust. It breaks through in the crust, and it comes out as a jet, what we call a cryovolcano. Okay, so it's not like any volcano on Earth. We certainly wouldn't expect to see water jetting up and making a volcano here on Earth. I would hope not. But that's what's happening here, because now the temperatures are so cold that any heating mechanism, in this case frictional heating due to tides on Enceladus, is causing water to heat and then generating vapor pressure and forcing its way up to the surface and causing these jets. Pretty cool, to say the least. And here's another great background. You can actually see some more of the jets coming off of Enceladus. Okay. Another great picture. So we talked about craters before. You say, oh, gee, look at all the craters here. Sure enough, this suggests that certainly this part of the surface of Enceladus is pretty old, because there's lots of craters, right? Okay, but look at this part. There's no craters there. It's got to be a new surface, right? So again, there's probably water underneath there. It's forming these jets, and in fact, there's cracks along here. And I'm not certain which crack it is. It might be one of these things or one of these things, where basically it's a fissure where the water has found a place to come up. It's a weak spot in the crust, and it's spewing out and causing these jets here. Okay. The water falls back as snow. So it snows other place. In Enceladus, it snows. And some of it does get added to Saturn's ring. This comes from the Cassini-Huygens spacecraft. Okay, Saturn. Actually, I talk about Saturn in my petroleum engineering course, because lots of lakes of hydrocarbons. Holy crap! Pretty cool stuff, right? So that doesn't necessarily have anything to do with the volcanoes, but it's a great thing to talk about it in Titan. Matter of fact, there's talk about, oh, we should send a probe to Titan and actually have a submarine going into these lakes. These lakes may be as deep as, oh my gosh, 1,000 feet. It's remarkable. There is one lake, I can't remember the name of it. It holds more liquid, whatever that liquid is, hydrocarbons of some sort, more than all the Great Lakes combined. So pretty amazing. This right here is in fact a feature. You can sort of see it's circularly. It is in fact a mound that somehow there's some pressure coming up from underneath and causing this to push out. They think it may be pressure from methane that's causing the surface to push out as like a dome structure. Okay, sort of interesting. Not a volcano, but sort of cool. No plate tectonics, right? Nothing like that. Neptune. What does Neptune have to anything to do with it? Well, there is some hint of an atmosphere. It's still a gas giant. It's really far away. It's very cold. But one of the moons, called Triton, has what looks like volcanoes, and it looks from a Voyager 2 flyby. When you look at this is Triton. There looks like these things here that what's going on here? And as they did the analysis, they realized, oh, there might be, in fact, nitrogen driving material out of the core and then depositing this black stuff. It's almost like downwind in a sense on the surface. Okay, and so again, they're cryovolcanoes. They're not water anymore, but they're much, much colder. nitrogen driven. Okay, pretty cool. So Pluto, ultimately ice, right? And again, you start seeing all these craters. So at least there's some surfaces on Pluto that are very ancient, and then others here that are relatively new. It's you know, hydrodynamics, if you want to call it, that it's difficult for us to comprehend. They have mountains of water ice and glaciers of frozen nitrogen. I mean, remarkable. There's no necessarily any volcanoes on Pluto, but it's an interesting thing to talk about because it's so different than what we're used to seeing here on Earth. But there are a lot of interlopers that come in from the Kuiper Belt, and we call them comets, right? And so traveling deep from outer space, all of a sudden this head of a comet comes in, and look at this. What is going on here? So apparently there is water underneath, our best estimate based on telemetry, and it's gotten heated up by sunlight. So sunlight is coming in onto it. Sunlight is here, okay, and it's heating up the surface. And it's causing material that it actually is coming out and spewing water out. And so is this a cryovolcano? I don't know. Is it fire or ice? Interesting. So that's about it. This is my last slide. It's a great pre-picture.